My name is Anup Rao. I'm going to tell you about our work XOR Lemmas for communication via marginal information. This is joint work with my student Siddharth Iyer. So here's the basic question we study. We want to ask, if f is hard to compute on one input, is f harder to compute on n inputs? Now that's a question you can ask in any model of computation. Sometimes the answers are very interesting. Given a function f, let's write f plus n to denote the n-fold XOR of f. Okay, that's a function you get by evaluating f on each of its inputs and then taking the XOR of all of the outputs. And let's write fn to denote the concatenation of the outputs. So here are two classical examples where this question has an interesting answer. The first is Yao's XOR lemma. Yao showed that if you have a function which has a feature that it is hard to compute, meaning that every circuit of size s can succeed in computing f with probability at most 2/3 on a random input, then if you take the n-fold XOR, that's going to be even harder to compute, at least for a smaller circuit. Okay, so he showed that if you take a circuit of size roughly epsilon squared times s, then the probability of success drops down to close to half. So this is Yao's famous XOR lemma. So that's a result that says that somehow when you take the n-fold XOR, it becomes harder to compute. And another interesting example comes from the algorithm for matrix multiplication. So it's easy to show that if you that there is a n by n matrix A such that the function f of x, which is equal to a times x, is hard to compute, in the sense that every circuit C of size roughly n squared over log n will be unable to compute, will have probability of success in computing C that's bounded away from 1. Okay, you can show that using a counting argument. You can count the number of matrices, there's 2 to the n squared of them, and then you can count the number of circuits of size n squared over log n and reason in that way. On the other hand, if you think about what it means to compute f the n of x, okay, f on n different inputs, that corresponds to multiplying 2 n by n matrices. And we can do that in time order n to the 2.35 or something smaller. So that gives you an example of a function where computing n copies is significantly easier than computing each one separately. Okay, so interesting things happen with circuits. A setting where you can ask this question where we understand the answer completely is in the context of sending messages. Okay, so you can ask, if you have x coming from some distribution and it's hard to encode x, then what can you say about encoding n independent samples from the same distribution? Well, Shannon answered this question completely. Okay, because the encoding length for the n copies is essentially determined by the entropy of the n copies. And if the n copies are independent, then the entropy adds. Okay, so there's no clever way to compress n independent samples from a distribution. Okay, at least in terms of the expected length of the messages you send. Okay, so that's a setting where we understand this kind of question. Now, we're interested in studying this question in the context of the model of communication complexity. I will not formally define the model of communication complexity, but I'll just give a high-level introduction to it. So in communication complexity, you have two parties, one who has an input x and the other has an input y. These are, think of them as n-bit strings. And they're trying to compute some joint function f of their inputs. And in order to do this, they come up with a protocol that describes how they will communicate messages back and forth about their inputs. And these messages should determine the value of the function f. The measure we're interested in is the length of the conversation that they need to have in order to compute f. Now, the reason communication complexity is interesting is that it is, in a sense, a core model for computation. Okay, so here's my analog of the Church Turing thesis for communication complexity, and I really believe this to be true, that every form of computation, every computational model inherently involves communication in one way or another. Okay, that's something I believe to be true, and in fact, it's borne out by the history in the last 3 decades. So there are all kinds of computational models, these models that are listed on the right-hand side here, which inherently encode some kind of communication protocol in them. And the nice thing about communication complexity is that the model of communication complexity is very simple and very amenable to attack with tools from mathematics, old tools from mathematics. And so communication complexity sort of forms a conduit, a link to apply all of these old ideas in math to models of computation that we care about. So many results in the study of these models on the right-hand side are proved by appealing to results about communication complexity. Okay, so it's a core computational model. And we're interested in asking the question we talked about in the model of communication complexity. So I want to know, if f is hard to compute, is the n-fold XOR of f even harder to compute? And is f to the n copies of f, is that even harder to compute? So as before, I can define the n-fold XOR of f and f to the n like this. And throughout, it'll be helpful to define the quantity, the advantage of f against C-bit protocols. This is the maximum advantage that any C-bit protocol can have for computing f on the worst input. Okay, that's what this quantity measures. So the advantage is always at least 0, because if the protocol simply outputs a random bit, then that would give you 0 advantage. But in general, what we're measuring here is what is the best protocol with C bits of communication? What can it achieve? Okay, how much correlation can it achieve with the value of f? The maximum advantage you can achieve is 1. So if the protocol computes f perfectly, then it would have an advantage of 1. So the advantage is the number between 0 and 1. The first general result along these lines was proved in my joint work with Barak, Braverman, and Chen in 2009, where we showed that if C is at least 3, and if the advantage of f for C-bit protocols is bounded away from 1, then the advantage for the n-fold XOR is also bounded away from 1, even with communication that's larger than C, even with communication that's roughly square root n times bigger than C. Okay. And I should say here, some kind of assumption of the type C bigger than or equal to 3 is necessary, because there is a counterexample. There is sort of a trivial counterexample. If you think of f itself as being the XOR of 2 bits, so f of x1, y1 is x1 XORed with y1, then you'll see that the n-fold XOR can be communicated with 2 bits of communication. Okay, you can think about that. So when f itself is the XOR, then the communication complexity does not grow. So somehow we need to exclude that example. In this result, that example is excluded by insisting that C should be at least 3. Okay. So that was proved in 2009, and then 4 or 5 years later, in joint work with Braverman, Weinstein, and Yehudayev, we proved that the advantage is exponentially small for similar setting of parameters, at least for f to the n. So if you want to compute n copies of f, then the advantage drops down to exponentially small. And the bound on the communication is the same as before. Now, recently, Huacheng Yu proved a very interesting result. In 2022, he showed that you can get exponentially small bounds for the advantage of the n-fold XOR of F, at least for bounded round protocols. So if you have a protocol that has only R rounds, meaning that there are messages in total, then he obtained some bounds where now the communication scales like C over R to the R times N. Okay, but the key point is that you obtain exponentially small bounds in this setting. Okay. And in our work, we prove results, the first results with exponentially small bounds for the general setting for arbitrary communication protocols. We prove that if C is bigger than some small constant, then and the advantage for of F with C bits of communication is bounded away from 1, then again under the old kind of bound in the communication complexity, you get exponentially small upper bounds on the advantage. Okay, so with at least with squared n times more communication, the advantage is exponentially small. That's what we prove. In fact, we have results for many other settings. So, for example, in the case of, if the assumption, if you're in the average case setting where the inputs are drawn from a distribution and that distribution is a product distribution, then we even get exponentially small bounds even if the communication is increased by an almost linear factor. And in the setting of R-on protocols, the case that you studied, we get improved bounds. So instead of an exponential loss in R, we just have a linear loss in R. Okay. So those are our results. Now, how do we do it? Well, the key idea of our work, it's in some way connected to this example of Shannon's that I talked about earlier. Now, what Shannon did here to think about this is come up with a notion of information, namely the entropy of a message. And this notion has some kind of subadditivity property. Okay, that's very useful to understand. And that's exactly what we managed to do in all of these results. So at a very high level, what we will do is come up with an appropriate notion of information, okay, which I'll talk about for most of this talk. That's what I'm going to spend my time talking about. And once you have this notion of information, the proof of this result has 3 steps. We show that every protocol with exponentially small advantage for computing the n-fold XOR eventually leads to a protocol for computing just F with constant advantage. Okay, so such a reduction will eventually prove this result. Okay, a protocol for the n-fold XOR with exponentially small advantage leads to a protocol for F with constant advantage. That's what we prove, and we do it in 3 steps. In the first step, we show that starting from the protocol that has exponentially small advantage for computing the n-fold XOR, we obtain that the protocol has information under some notion of information, which is bounded in terms of the communication complexity of the protocol. That's step 1. And then in step 2, we prove that any protocol that has a certain communication and small information for computing the n-fold XOR yields a protocol for F where the information goes down by a factor of roughly n. Okay, so this is the analog of the subadditivity in Shannon's argument. So the information is subadditive. And then in the final step, we show that any protocol with small information yields a protocol that actually has small communication. Okay. So those are the 3 steps of the proof. And the crucial ingredient in all of the steps of the proof is what is the notion of information that allows you to actually carry out all of these steps. Okay, that is the difficult thing to come up with. And it's famously a very subtle problem, because whenever you come up with a notion of information, it has to work through many constraints. It has to work for many constraints that allow you to carry out all three of these different kinds of steps. So I'm going to talk about now how we got to the notion of information that we work with. That's what I'll talk about in the rest of the talk. Okay, so given our high-level strategy, now we're left with trying to find an appropriate way to measure the information. And this is what is referred to as information complexity. So we have a protocol. There's some input X, input Y to the two parties. And the parties are somehow generating messages that they're exchanging with each other. And we want to measure how much information is revealed by these messages. Now, when I started the talk, I was thinking about worst case complexity. So I was thinking of X and Y as worst case inputs. And the distribution is only on the messages. But when I want to talk about information, I want to switch to the average case setting. So I imagine that there's a distribution on inputs X and Y, and then a distribution M on messages that are correlated with X and Y. Okay. And you can go back and forth between the worst case and the average case using Yao's min-max theorem. Okay. So from now on, imagine that there's a joint distribution on inputs X and Y that we're working with. And let's write P of XYM to denote the joint distribution of all the variables, the inputs and the messages in the protocol. Okay, so given any protocol, there's this distribution P that describes the protocol. Now, the first attempt to define a notion of information was made by Chakrabarty, Sheworth, and Yao. And they were thinking exactly about these kinds of questions in 2001. And they defined a concept that I will refer to as external information. They didn't call it external information at the time, but now it makes sense to call it that, to contrast it with other definitions. Okay. And their concept was to measure the mutual information between M and XY. It's a very natural concept. You try to measure how much information is revealed about X and Y from M. Okay, and you can think of it as how much information is revealed to an external observer. Concretely, this quantity is equal to the expectation of this log ratio, the log of P of XY given M divided by XY, where the expectation is taken over all triples XYM. In 2009, Barak, Braverman, Chen, and myself used a different definition. We used a definition that we called the internal information. And the internal information measures how much information is revealed about the inputs to the parties. The parties already know X and Y. At least each of them knows one of the inputs. And what this quantity measures is how much information is revealed to each party about the other person's input. And if you work out what this quantity means, it measures the expected log, the sum of the log ratios of two quantities, each of which corresponds to the amount of information learned by one of the parties. Now, these definitions have a long history. In fact, right before I worked on this topic, I was working on proving results about the parallel repetition theorem, a very important result in complexity theory. It's connected to understanding PCPs. And in the proofs of the parallel repetition theorem is a formula that is very similar to this formula. Okay, and that's where this formula came from. So in fact, the proof that we came up with in Barak, Braverman, Chen, and my work used both this kind of definition, which came from parallel repetition, as well as other concepts, the concept of correlated sampling, which was also developed in the context of parallel repetition, and we adapted those ideas to this setting. Okay, so that's where those ideas came from. In 2013, when Barak, Weinstein, Yehudayev, and myself proved our exponentially small bounds, this exponentially small bounds that I mentioned for computing n copies of f. So we took the infimum over all proxies q, where q is close to our intended distribution p in L1 distance, and then we measured the information according to q. So this distribution q is no longer a protocol. It can be some crazy distribution. And now I will come to describe our distribution in the current work. And our distribution and many of the ideas in our paper are inspired by this recent work of Huacheng Yu, where he proved results for bounded round protocols. And a key observation of that Huacheng made is that he defined the concept of a rectangular distribution. A rectangular distribution is somehow like a restricted family of distributions, kind of like a protocol, but it's not as restricted as protocols. Okay, so it's halfway in between an arbitrary distribution and a protocol distribution. The definition is very simple. So we'll say that Q is rectangular with respect to P if Q satisfies this formula for some functions A and B. Okay, so Q has to look like the probability of xym has to be the product of the probability of xy according to P, and times two functions A of xm and B of ym. Now a protocol distribution does satisfy this property. So every protocol distribution is rectangular. Okay, that's easy to see. But the space of rectangular distributions is much bigger. So what is our definition? It looks like this. Okay, there are a few differences from the old definition. So we take the infimum over all q that are rectangular with respect to P. And then for each fixed q, we take the supremum over all triples xym of the following log ratio. In the log ratio, the first two terms, they correspond to the old internal information terms. Okay. I should say there's also a parameter I throughout here. So think of I as some fixed parameter. Okay. So the first two terms in this definition correspond to the internal information terms. The third term, it corresponds to ensuring that Q is close to P, in the sense that the Q over P ratio is controlled. And the last term corresponds to ensuring that the advantage for computing F under Q is large. Okay, so these are the terms in the information measured. And what we're doing is taking the maximum of the log ratio of all of these quantities. So any, for particular, the information can be small, even though any one of these terms is actually quite bad. So for example, you could have a very large contribution from the first two terms as long as that's compensated by the contribution from one of the other terms. Okay. So we've picked this definition, and another big difference is in the previous definitions there are expectations, whereas here we're sort of taking the worst case log ratio. Okay, that's something we can afford to do. So given this definition of information, we're able to execute all three of the steps of the high-level approach. Here again, to recap, is our result. We show that if the advantage for computing F with C bits of communication is bounded away from 1, then computing the n-fold XOR of F, even with squared n times more communication, your advantage is at most exponentially small in n. And I think the biggest open question for all of these questions is to obtain such results even with a linear or nearly linear blow up in the communication.